in a very natural way. This is actually not an accident, and we'll say more about that as we go. The second part of this, I want to talk about this, is what does this have to do with supersymmetry? And so I'm going to talk about this in the second hour. So we'll start again doing pretty much what I did in the first hour, except much more generality than supersymmetry. Except I'm going to analyze the supersymmetry aspect of this. But before I do that, I want to point out another very important feature. First of all, as rho goes to infinity, h goes to 1, and the metric goes, of course, to flat space. As it ought. We're thinking about this as a localized lump in flat space. The other very generic feature I want to pull out of this is that when you look at rho going to 0, then h goes like q over rho, q over rho. And now you see a slightly different structure. You see the metric goes in the following form. The h cancels that, and you get d theta squared plus sine squared theta d phi squared with a q squared. The rho's cancel. And then the other part of the metric, let's see, we get something like a q squared. I'll put it out as a factor, d rho squared over rho squared. And then you see from h minus 2 that produces a q in the bottom, something like q to the minus 4, dt rho squared dt squared. What you're supposed to see is, as you approach the horizon, the sphere is stabilized to a fixed size. This is an S2, a radius q. And this is ADS2, the antipacific analometers. And its scale is also set by q. What's actually happening is that as rho goes to 0, basically the electromagnetic field is also similarly F, walking to the volume form of the ADS2. So very, very close to the horizon, the two form that is the Maxwell field becomes the volume form of this ADS2. But the metric breaks into a direct product of a sphere and an anti-de Sitter space. And this is absolutely generic for all extreme solutions. There's always an ADS cross a sphere. And this is really the horizon, or what's going to become the horizon, and then this is the asymptotic approach to the horizon. This is historically called the Robinson-Bertotti metric. But it is the near horizon region of this black hole. So what I'm trying to do even though this is a very specialized example, is I'm trying to pull out the general threat. And this is another very important general threat. That in the limit, near the horizon region of any of these objects, you wind up with a anti-de Sitter across a sphere. Okay. So what I'm going to do now is start right back at the beginning again. But I'm going to do, motivated by this form of the metric, and I want to think about the most general supersymmetric solution that basically has this form. I could make it more general, but for the purpose of this class, I just want to keep it relatively simple. I'm going to take the metric to be the form is equal to minus h to minus 2. I'll say what h is a function of in a minute, plus h squared y dy dot dy. H is an element of, y is an element of R3, flat space. And h at the moment is going to be an arbitrary function. Moreover, I'm going to take the most general possible time-independent electrostatic potential. So A, the potential is going to be some potential function times y. The paper that's relevant here is an old paper by Gibbons and Hull. I was originally basing the lecture on this, and then I discovered there were mistakes in the paper. I'll explain that in due course. Gibbons and Hull references in the notes. But the goal is to look at the most general supersymmetric solution of this form. We will recapture that solution, but we'll get a lot more. We'll get, ultimately, what I call the drummed up hypervectory. Well, I want to do this very gently and slowly because we will use this kind of algorithm a lot. The other reason I want to do this is because one of the core messages I want to make is that solving supersymmetry equations is much easier than solving equations of motion. The exercise I did in the first half, solving equations of motion provides an Nordstrom. It's relatively easy. You can do it in half an hour. And it took 4 years since Einstein's equations to actually get the solution. But the minute you get more variables, more dependent on more directions, and you don't insist on spherical symmetry, it gets really, really hard. The most general axisymmetric solution, not even the most general one, but the one that's most physically relevant, the rotating black hole, wasn't constructed until 1963. It took another 43 years. That's the degree of difficulty of getting to things that don't depend on, well, depend on more than one variable. Supersymmetry makes things much, much easier. So as I say, it's a Faustian bargain. You also get the zero Hawking temperature. So let me explain what we're going to do. So for those of you, I'm not going to assume you need to know very much about supersymmetry, but let me just explain why it goes into this discussion. Supersymmetry is a symmetry of bosons and fermions. So you have a supersymmetry variation with a parameter epsilon of a boson, and it becomes epsilon times a fermion, is the generic form of this thing. And there could be derivatives, I don't care for the moment. And if you do a variation of a fermion, it becomes epsilon times a boson in your theory. If you have such a symmetry of the Lagrangian, and you can make that work, then basically you have a supersymmetric theory. And things that aren't supersymmetric can often be supersymmetrized, and so generically a BPS, the notion of a BPS object being the lowest energy state within a sector of a theory can actually be given supersymmetric flesh by supersymmetrizing the relevant theory and then saying, well, what are the supersymmetric states? The answer is the BPS states. So supersymmetry is almost synonymous with BPS, but it's not a theorem, it's just generally a practical fact. Okay, so you've got a theory of such a symmetry, and you look for backgrounds that are purely bosonic. Bosonic. And the question is, do they preserve the supersymmetry? And you usually abbreviate supersymmetry as SUSY, do they do that? So, okay, it's purely a bosonic background. That means the fermions are identically zero. And if you want to preserve the supersymmetry, you would like this to be zero. That's what it means to preserve some supersymmetry. The variation of the background has to be zero, otherwise you've broken the supersymmetry. But if the fermions are identically zero, there's nothing to check here. The only thing you have to check there, I will leave that. The only thing to be checked is then to solve the equations delta of the fermions is equal to zero. So generically what you do is you go to your favorite supersymmetric theory and you look at the variation of fermions and you set them to zero. And those are the supersymmetry equations. Now, what we're looking at here is in fact Einstein theory coupled to electromagnetism. We have a metric and we have a Maxwell field. And the basic, simplest theory that contains that is called n equals 2 supergravity, which is what this paper is all about. I'll explain this notation, so all of this is going to be a discussion we're going to have about what that means in due course. But for the moment, it is the simplest supersymmetric theory that has the bosonic content of a metric and a Maxwell field. It has some fermions, which are the gravitini, 2 of them, that's why the n equals 2, which will play a role in net. So there are 2 of them. Or equivalently, and I'm going to think of it simply, this is a Dirac fermion. So there's an additional Dirac fermion that carries a spinor index. It doesn't really matter. You just dig into the theory. You're going to try and suppress much of these sorts of details in this course because you could spend the whole life just messing around with this one theory. So as I said, the thing we have to solve
Some people have.
is delta psi mu. And you go look it up in this theory, and you find that it is nothing other than the covariant derivative of the spinor parameter. And I'll write down in factors like this. So, there we go. It's, here it is, 1/4 f rho sigma, gamma rho, gamma sigma, gamma mu, epsilon. So basically, supersymmetry tells you that if you want to have supersymmetry, you have to solve that equation. It is saying that I've got a bosonic background made of metric and made of electromagnetic fields. I want to make sure that it preserves some supersymmetry. I have to look at the other fermions of the problem, their variations, and I have to solve this being 0, and then I'll have a supersymmetric solution. So, supersymmetry requires that I solve this equation, where epsilon is a Dirac spinor. So that's what we're going to spend a little bit of time doing. But I need to perhaps talk about spins in curved space a little bit. But basically, at the end of the day, all it's going to mean is that we solve this class of systems. And the first thing to notice is this is a first-order differential equation. Whereas the equations of motion are second order. Okay, so it's much easier to solve this class of equations in principle. So the first thing that supersymmetry buys you is you're solving a first order system, not a second order set of equations. That's a huge simplification. And we're going to apply it directly in here. Any questions after I go there? So now, I have to I only want to assume that you know about Dirac equation in good old flat space. So let me just tell you what to do here and how to interpret this. We have a metric.
Sorry, stupid question. Why delta epsilon boson is automatically satisfied?
Because it's equal to a fermion. Delta epsilon of a boson.
Equal to 0.
Delta epsilon of a boson is epsilon times fermions.
Yeah.
And all the fermions are set to 0 in typical backgrounds.
Yeah, but why delta epsilon boson equal to 0?
So where's?
No, this is what you ask. This is what you ask, but why it is satisfied?
Because the right-hand side of this equation is always pure fermions. So let me give you an example. If I take the variation of the metric,
I don't understand what you're saying.
Supersymmetry, it's something like epsilon bar, gamma mu, psi mu, symmetrized.
Okay, I understand.
You set all the background fermions to 0, and that's 0.
Okay.
But generically, now that's a great question. Generically, so the interesting ones are the other guys because they vary into things that aren't set to 0. So therefore, you're going to get differential constraints on those things. But these are automatically satisfied. Unless you have a Gaugiano condensate or something more exotic, these things are all 0. So you get that for free. Okay. So the first thing to realize is this is an amazingly useful first order system. Now I'm going to be a little bit more pedagogical about how you handle this. So everything here, we're in 3 + 1 dimensions, so this is a Dirac fermion, so if you know the Dirac equation, you can solve this. But there's one little subtlety I had to say about, we're in curved space-time. We have a metric. Okay, so now, the first thing you do is you introduce frames. So turn everything into flat space. Or at least turn the spinor business to flat space. You introduce a frame which I call EA mu. And the whole point about EA mu is that if you take the Minkowski metric, by definition, G mu nu. This is the Minkowski metric. This is diagonal minus 1, 1, 1, 1. Okay, so you introduce frames. In this case, you just do the obvious thing. The zeroth frame, mu, is simply dx mu, is simply going to be h to the minus 1 dt. And the I frame mu dx mu is equal to h times dyi. So what I've done is I've introduced these objects which convert the Minkowski metric into the general metric. And when I write a gamma matrix, gamma mu, what I mean by that is something which is the frame contracted with the gamma a's like that. And these are the absolute standard gamma matrices that you learn in Dirac theory. So if it carries an index which is a space-time index, it is a complicated beast, the gamma matrix, but everything in here is implicitly a standard gamma matrix contracted with a frame. Okay? The next thing I have to do is to tell you how to take the covariant derivative. So I have to unpack this term. So I need, having got the frames, I have to introduce a spin connection. I've got 20 pages of notes. I use this in a GR course I can give anybody who wants them, about all kinds of issues here. But basically, the first thing I do is I'm going to define the covariant derivative on epsilon is equal to the partial derivative of epsilon plus an appropriate connection term. That's the definition of covariant derivative of epsilon. What is omega mu nu? Omega mu nu, AB, is defined by simply requiring the covariant derivative of the frame is 0. The way you define this correctly is d mu of the frame plus, now you take the covariant derivative on the frame index, so I'm taking value u, that's your A, B, let's see, times E, B rho, and then of course the standard connection on the usual index, which is, we've got a rho, so we'll take a mu, mu rho, E, mu rho, E, mu, A, mu. That must be 0. So here's the partial derivative of the frames. I've written the frames for you here. You take the partial derivative of the frame, you take the standard Christoffel connection, and that defines for you the omegas. Now, why you do this, that's a much longer story. And as I said, I've got a pile of notes, but essentially it makes the idea of frames consistent, or the covariant derivative of frames consistent with the covariant derivative of vectors and things like this. Let me give you a 30-second comment about that. Given the spinner, I can construct a vector field, say by doing that, or a tensor field by doing more. You would like the covariant derivative of spinners on this side match the covariant derivative of vectors on that side. This is the definition that makes all of that work. I've got a pile of notes I can give you if you would like a much more detailed explanation. But basically, here's the rule. We need to have covariant derivatives of spinors. The way you define a covariant derivative of spinors is through the appropriate connection on spinors. The appropriate connection on spinors is made in a very standard way by saying, I would like these frames that I've introduced that turn flat indices, Minkowski indices in space-time indices, to actually be covariant constant. And then I deduce what this is. It's in the same way that when you first do GR, you impose that condition, and that tells you what the Christoffel symbols are. Same deal here, except you now got this sort of spinorial flat index, and you want a connection on it, and it is defined in this way. And raising and lowering of these indices is done with eta. Okay? So, I've told you very quickly how to unpack this, but this is the equation we want to solve. And so let me go back to the metric of interest and before any questions. So I'll leave you with an exercise to make sure you understand. The exercise is to compute the spin connections with this set of frames. They're in the notes. I didn't actually derive them, but it's relatively easy to do. And you find the following. Where's it gone? Spin connections are. Down says omega 0, or we define omega AB to be omega mu AB contracted with dx mu. So you get the space-time index and contract. And you find that omega 0I is equal to minus omega I 0 is equal to h to the minus 2 di h times the frame E0. And omega ij is equal to minus omega ji is equal to minus h to the minus 2 of di h ei minus dj h e upstairs I takes values 1, 2, and 3. And when I write EA, I mean EA times mu dx mu is a 1 form. So basically, it's a relatively straightforward calculation, but let me sort of explain how it comes about. In the notes, I've given the Christoffel symbols. Here you're differentiating the frames, but look what the frames consist of. They're basically h's or h minus 1s or h's. So it's hardly surprising that everything in this piece here has to be some derivative of h. And if you work it all out, it's that. Okay, so what are we going to do now? We're going to solve this equation. Put that board out of the way. Good. So, I'm going to write. And it's easier if you turn everything into spinor indices. I've still got my Maxwell field in there, I hope. Maybe I've obliterated it. Investigation A is equal to phi y times dt. Okay, so I'm going to introduce, let me just call it V of C. I'm going to write everything in terms of frames. This is the inverse frame of delta psi mu. This guy has the property that E mu C, E A mu is delta A C. And now you write down what you get. So let me write down the components. What I call V naught. The zeroth component of this equation is some problem from S. It is H. I think that's a bit of room, but maybe it's good enough. dt of epsilon plus h minus 2 di of h times gamma 0 gamma I epsilon plus 1/2 di phi of gamma 0 gamma I gamma 0 epsilon, and vi is equal to h to the minus 1 di of epsilon plus 1/4 h to the minus 2 j h gamma j gamma I minus gamma I gamma j of epsilon minus 1/2 dj phi of gamma 0 gamma I epsilon. Okay, let me explain where this came from. So basically I've got an inverse frame in here, so I get an h or an h to the minus 1 depending on which way I'm going. So basically in dt case, I get, when I get ddt, I get h to the minus 1. That's wrong. I think probably not an h, so it's h, so let me see that. That's, oh, that is h, good. Okay, so the inverse of the frame 0 has an h in it. So there's an h here, then I get ddt of epsilon. Then I get some spin connection crap. Here's the spin connection crap. It's di of h, h to the minus 2. There's an E0, and omega I0. So the E0 tells me I'm looking at the 0th component of it. And then I get omega 0I, gamma 0, gamma I. I have a quarter from the connection, and I've erased it, but there's a quarter, omega mu AB, gamma A, gamma B. I get a quarter, but I get the index in both orders, so it gives me a factor of 2. So I get a half of this thing, gamma 0, gamma I. There's a 0I here, times epsilon. So that's this first term, wherever it's from, spin connection piece in here. And then in here, the last piece is I get, remember, F is equal to di of the potential dt wedge dyi, which is actually di of phi times E0 wedge EI. So it has a 0I component, which is di phi I with gamma 0, gamma I, gamma 0, gamma I, and then gamma 0 because I'm taking the 0th component. So basically, the first equation, you just read it off from the spin connection. Second equation, the same deal. Now what I'm looking at is I'm looking at di of epsilon. This index is I. Inverse frame gives me h to the minus 1. And then I look in the spin connection part, and here it is. Signed, I think it correct, as a quarter. And then I get gamma I, gamma, oops, I think that's J. Gamma I, gamma J, gamma minus gamma J, gamma I, written in that order, except I've written it in the right order, times epsilon. And then I go to the Maxwell field strength term, and I'm looking for the I component, and I get di, let's see, I'm looking for the I component, my indices should contract. I write down F0, let's see, I'm looking at the I component of the Maxwell field, which gives me an I component of this guy with a 0. So I get gamma 0, gamma J, contracted with J, and then gamma I left over. Good. Because this is the full contraction here, and that's the result. Okay? So those are the equations you have to solve. And this is now written in terms that are, in some sense, no more mysterious than the Dirac equation. Right? Happy? Good, Anthony? Okay? So, he's the only guy I know who's a real honest graduate student, so therefore. Questions? So, this first order system, I didn't say it was going to be simple, but if you know what you're doing, it turns out it really is simple. We have to solve this to get the supersymmetric solutions. Okay? So that's what we're going to do. And we're going to be a little bit smart about it. So now we can get rid of the whole thing. Except keep this part and get rid of everything else. Now, usually, the easiest thing in the world to do is to solve the 0th, the time-dependent component. Because, almost without exception, although there is an annoying exception for anti-de spaces, we can assume, to make life easier, I'm going to look for solutions. It's hard to prove these are the only ones. So I'm going to make some inspired guesswork. But since it's time-independent, I'm going to assume the spinner is time-dependent. That's dangerous, but it's actually true in, for this class of solutions. For anti-de there might be some time-dependent ones as well. So, since we're static, or time-dependent assumes is true. And therefore, we get the first equation becomes rather simpler. And I'm going to pull out some factors. I'm going to pull out a half. I'm going to put gamma 0, gamma I is going to come out as a factor. And then I'm going to get h to the minus 2 di of h, and then this guy plus, up to the sign, 1/2 di of phi, gamma 0 acting on epsilon is 0. That's what we have to solve. Okay? Now you can amuse yourself by getting rid of the gamma matrices by multiplying by gamma 0 and gamma I, and it kills off these terms. What we have to do is solve this. And there's an obvious solution. Remember, gamma 0 as a gamma matrix squared is 1. It also is traceless. Okay? Dirac matrices are traceless. It's traceless and squares to 1. Therefore, its eigenvalues are plus and minus 1, with eigenvalue with equal numbers, 2 plus 1s and 2 minus 1s. So the obvious way to solve this, oops, the half has gone out the front, is to simply declare that di of h is equal to plus or minus phi, di phi, and then required gamma 0 of epsilon is minus or plus or minus, I'll get the sign right in a minute, I think it's minus or plus epsilon when you solve this equation. So, minus or plus. You solve this by saying this function and this function are the same, or up to a side, and then gamma 0 of epsilon is plus or minus epsilon, because gamma 0 has eigenvalues plus or minus 1 in equal numbers.
So what is h minus 2?
H minus 2, sorry, H minus 2. With a minus sign, yeah, something like that. So the point is, I should have written this as di of h to the minus 1. Thank you. But look at what we've just got. What we've learned is two things from that equation. I'm going to keep the second one, but let me obliterate the first one. We've solved the first one by simply saying gamma 0 of epsilon is plus or minus epsilon, and phi up to a constant, is plus or minus h to the minus 1. With the signs. The signs are correct in the notes, I think, but the point is this sign and this sign are correlated. Okay, so two things to note here. First and foremost, supersymmetry, what has happened? There's this metric quantity, g naught naught, is equal to h to minus 2. And in the Newtonian approximation, it's 1 plus 2 phi over c squared. Well, that's the Newtonian potential. This, therefore, contains the mass. Phi is the electrostatic potential. The rest of the A is equal to phi t. So the very, very first thing we learn from supersymmetry is that the electrostatic potential is locked to the mass. This is, in a very general sense, Q is M. Whatever we're going to get is Q is M. It comes in the very first step of solving supersymmetry equations. It locks masses to charges, and it happens because you have to have a non-trivial translation between the spin connection and the electromagnetic field. And it came from basically that matrix equation. So first, really important takeaway point, supersymmetry locks the Coulomb potentials to the mass terms, or the metric terms. Okay, so second thing, the next things are just a little bit of tedious hard work, but it actually reveals something else. Oh, the second thing, okay, let's say the second thing we've learned. Oh, shit, I'm wasting the equation, but I'll come back to it. We're going to solve the remaining equation. It'll go, but it goes in a, let me put, so that's mass equals charge. Supersymmetry requires that. What does this do? It reduces the amount of supersymmetry. So let me get rid of this lot. Okay, so gamma naught epsilon is plus or minus epsilon. Let's pick a definitive sign, say plus and phi is equal to plus h to minus 1. Pick one sign. What does this do to the supersymmetry? Remember, gamma naught squared is 1, trace of gamma naught is 0, so therefore gamma in some basis is 1, 1, minus 1, minus 1, in some choice of gamma matrices. So what does this do is this cuts the number of supersymmetries in half. It is a projection condition. The takeaway message is, generically there's always a projection condition. On the spinners. And often, but not always, it cuts the SUSY in half. It may do worse, it may do less, but roughly speaking does that. There's always a projection condition. And it says, a priori I had Originally I had 4 Dirac fermions, or Dirac SUSIs. Now I have only 2 complex components. Precisely those guys that satisfy this equation. So you cut the supersymmetries from 4 complex parameters to 2 complex parameters. Or if you prefer, from 8 real parameters to 4 real parameters. There is a horrible terminology that goes with all of this. I think I'll keep that. No, there's a horrible terminology that goes with this. In a sense, but I'm going to make it much more precise, you'll hear this said, these solutions are sometimes called half BPS. This is a horrible term and I'm going to explain why in a minute. The half BPS, or the half when you hear it, refers to the half that's happening here, or the half that's happening here. The SUSY conditions give you 1/2 of all possible spinors. Now, nobody actually calls this solution half BPS for reasons I'm about to explain. The best way, the universal way to describe this solution is that this solution has 4, and usually implicitly mean real supersymmetries. That's unambiguous. You count the number of actual supersymmetries on the left. So how many supersymmetries? I start with the direct spinor, that's 4 complex components. The projection condition cut it in half, 2 complex components, 4 supersymmetries. Actually, this solution is usually viewed as what is called 1/8 BPS. Why the hell does 1/8 BPS? Because if you think of it as embedded in a maximal supergravity theory, it actually, which has 32 SUSIs to start with, 1/8 gives you 4. So the notion of half BPS, quarter BPS, 8 BPS is context dependent. And that's why it's a horrible terminology. If you know what the context is, it's absolutely clear. But the best way to say is this solution has 4 real supersymmetries and nobody will get confused. Because you count the total number of real supersymmetry parameters, the left. But in the context, it's sometimes called half BPS or 8 BPS, depending on how you've carved up the supersymmetries. And if you embed this thing in a maximum supergravity, this is actually 1/8 BPS. I'm not going to go there. In the context we're working, which is an n equals 2 supersymmetric theory, with a single Dirac spinor, it is a half BPS. Let's say contextually dependent. But 2 takeaway messages. There's always a projection condition on the spinners, and it cuts the amount of supersymmetry, often in half. Now, we haven't solved the rest of the equations. I've only solved the time-like component, but that's usually where all hard work, the heavy lifting is done. Let me go to the other component, because the other component is actually rather easily deduced directly. So let me write down the other equation. The other equation, actually, we have to work at. Okay, so the other equation was what I was calling VI, which is equal to h to the minus 1 di of epsilon plus 1/4 h to the minus 2 dj of h gamma j gamma I minus gamma I gamma j epsilon minus 1/2 dj of phi gamma 0 gamma j gamma I of epsilon is equal to 0. So now you use what you've learned. This is dj of h to the minus 1, and you also know that gamma 0 of epsilon is, say, plus epsilon, plus or minus, and you shove it in. And the end result is you get h to the minus 1 di of epsilon, and then you choose, there's a horrible dog's breakfast in equation 2.53, but never mind. Let me write down what the actual answer is. Minus 1/2 di of h to minus 1 epsilon is equal to 0. What I've done here is I basically pulled out, where did I get the gamma? I think I've got some gamma here. Oh no, that is exactly right. So let me explain what happens. There's all this gamma matrix crap, right? You have to deal with. But what actually happens is when you push this through here and replace this by epsilon, then this gamma j, gamma I, in fact, exactly flips this sign. With a net minus 2, it exactly flips this sign, and it becomes minus gamma j, gamma I, minus gamma I, gamma j, commonly known as 2 times delta ij. So it turns the gamma matrix into the identity matrix, gives you a factor of 2, and that's the equation you wind up with. So it's not so hard. You can solve that. Epsilon is equal to h naught, well, h to the minus half, epsilon naught when this is a constant spinner. Something which is non-zero, just make sure it's h to the minus half. I've lost it. Epsilon is h to the minus half, epsilon naught. Good. So this last equation is usually easily solved, and I'll explain why in a few minutes. But basically the hard, heavy lifting is usually the zero component, and then everything else just tells you how the spinner depends on space-time. Okay. Now we can play torus in a minute. The last class with this is, so supersymmetry has told us only three things. Let me summarize what they are. Supersymmetry has locked the mass to the charge, or more precisely, it has told us that phi is equal to h minus 1, up and plus or minus. It's given us a projection condition, and it's told us that epsilon itself is some constant spinner with an overall factor which depends on h, where this is constant. All the ordinary derivatives of epsilon 0 are 0. That's it. We've solved the supersymmetry conditions. So the thing to notice is we haven't solved the equations of motion yet. All we've learnt is that there's a relationship here, there's a reduction of the supersymmetries, and we know how they're parameterized respect to constant spins. That's all we've learned. So we can put in an equation of motion. Remember the metric, s squared is equal to h minus 1 t squared. Now, you get to choose because it turns out, I'm going to say something more about this in a minute. That's your metric. The Maxwell field, well, now we know that the maximum potential is h minus a half, so up to the side is minus di of di at h minus 1 times dt. And you want to calculate d star of f. Okay? Now, remember when you calculate the star, you've got to start messing around with square roots of determinants and things like this. But at the end of the day, if you put this to 0, it is exactly equivalent to saying that delta ij of dyj on h to the minus on h is 0. So in fact, oops, that's my chalk. When you solve this equation, it's completely trivial to do. You find out that the Laplacian on the R3 of h is 0. So to learn that h is a harmonic function, you actually have to use equation of motion. But it is, as at this point, a completely general harmonic function. It doesn't have to be. A single center spherically symmetric. It can be multi-symmetric, and I'll come to that in a second. So now, and it turns out that I've already solved one equation of motion, but it turns out that's enough. I've solved all the equations of motion. So let me make a comment about that. So let me summarize the solution. The full set of solutions is simply this condition, and now impose del squared on R3 of h is 0. This is a completely general supersymmetric solution. And I'm going to unpack what's in it in a few minutes, but I want to observe many things. So the top line is supersymmetry. The rest of it is the equations of motion. Now, there is a story here which is long and tedious and depends on specifics, but the following question occurs. If you solve the supersymmetry equations, to what extent have you solved the equations of motion? And the first thing you see from this example is you haven't solved them all. The top line is supersymmetric. This condition requires at least one equation of motion. I claim, and you can check, that it actually, I only check the Maxwell equation, but I claim it actually automatically solves the Einstein equations. And generically what happens is that the sort of general rule of thumb is that if you solve these SUSY equations, and you only need one equation of motion, it's going to be a cleverly chosen one, then you get all equations of motion. And in fact, if
it's a 0, 0 usually, right?
It's plus plus depending on 0, 0 in the Einstein. If you solve all the Maxwell equations, so I'm going to explain where this comes from in a second schematically, and then I'll explain how this comes about. But and sometimes if it's suitably complicated, you don't even need that. So basically, solving the supersymmetry equations does almost all of the solving the equations of motion, and in many cases it solves all the equations of motion. But this is one of the exceptions, and there are a few such exceptions. But I want to stress, supersymmetry almost solves the equations of motion, not quite. So let me explain how it comes about in this example. So here's the equation we solved. Alpha factors I'll try to remember. Sigma gamma mu epsilon is 0. We solved that equation. Okay? So let's imagine we write down the integrability condition for that first order equation. So what's the integrability condition? Well, the integrability condition is grad mu of epsilon. You calculate the commutator of the operators, and then you use the right-hand side to simplify it. So what does that produce? It produces a grad mu of 1/4 f rho sigma, let's see, f rho sigma gamma rho gamma sigma acting on gamma mu of epsilon, gamma mu of epsilon. That's what the first one does, and then you get minus the same thing with mu interchange. And you know that when you calculate this commutator, you know it produces this answer. Now, when this grad hits the epsilon, you use the equation again. So if you unpack what that is, let's keep going a little bit, we'll keep that. Let's unpack it a little bit further. Let's look at what turns up. We have grad mu of epsilon is equal to, now let me write it very schematically. You get derivatives acting on f's and gamma matrices acting on epsilon. But then you also get when the derivative hits here, you use the supersymmetry equation, so you get something which involves f and a bunch of gammas acting on epsilon. So that's the schematic form of it. If you do the very hard work, you see what this is. So let's now look at this side. The commutator of two covariant derivatives on anything is always a curvature. Now on spinner, it is r mu rho sigma gamma rho gamma sigma of epsilon. And look at what you've got. This integrability condition you know is satisfied. You solved the supersymmetry condition. You solved this equation. If you have a solutions equation, it automatically solves this identity. But if you look at what this is Riemann tensor, and it's related to gradients of f and f squared terms. If, for example, you take the gamma trace on this side, if you hit this with gamma mu, this actually collapses the Richard tensor. And this disappears, and this becomes f squared, the Maxwell tensor. So in particular, this implies many, almost all, all Einstein equations. And embedded in here are the Maxwell equations. So in particular, the fact you've solved this tells you that you have actually implicitly solved almost every single equation of motion there is. Now, the difficulty is that those equations come mixed with lots of gamma matrices and the projection conditions and everything else. So to see how many of the equations of motion you've got and whether you've got them all depends on disentangling this mess. And fortunately for us, many results have been proven about this. There's papers by Gauntlet where they analyze a lot of these supersymmetries. And for example, if you do this in N theory in 11 dimensions, you need to solve all the supersymmetry conditions plus one Einstein equation or one Maxwell equation. And once you start putting one Maxwell equation solution, it automatically, in fact, if you put in here the Maxwell equation, this term is gone, and then this just gives you the Einstein equations. So there are all sorts of theorems that tell you that if you solve the supersymmetry conditions, you have almost solved every single equation of motion by virtue of this integrability condition, but not quite all of them necessarily. It depends on how complicated the right-hand side is, and if it's sufficiently complicated, you can actually show that all the pieces are independent, and the only way to solve it is by the equation of motion. This is a very complicated way of telling you something that anybody in supersymmetry learns at the beginning, that Q squared of supersymmetry is the Hamiltonian. So if you solve Q squared, Q on a state is 0, then you've solved Q squared on the state is 0. Which implies you solve the Hamiltonian on the state is 0. Which is a sort of abstract way of saying solving the supersymmetry conditions is the same as solving the Hamiltonian on the state being 0, which means you solve the equation of motion. This is rather good because this is essentially a scalar object, but morally this is what's going on. This is Q squared. Two supersymmetries acting generates an equation of motion. So, supersymmetry is much easier and much simpler to solve. You might need to solve one equation of motion, but usually it's the Maxwell equation, which is much easier than solving the Einstein equations. So, life is much easier, first order equations, and so forth. I want to unpack what we actually have here to finish. I've got 5 minutes, okay. So what have we got? We have a solution which is ds4 squared, which is minus h squared dt squared, h minus 2, h squared dy, not dy. And we know that this is supersymmetric so long as the Laplacian h on R3 equals 0. So in particular, I can choose h to be a constant plus any sum of qj over y minus some yj. Nice harmonic function. Okay. Previously, I had h is equal to 1 plus q over rho. But this shows me I can make a solution to the equation of motion with arbitrary number of sources put anywhere I like. And each of these is a black hole. This is the multi-Blackhole solution. Masses equal charges with mi equal to qi. This is the Magenta-Tapepetri metric, which was discovered long before supersymmetry. It's hard work. But it's the multi-Blackhole solution. So what's happening in the solution is it's time independent. And what you've got is a bunch of black holes sitting there, and they all attract each other with the standard Newton-like force, if you like. But they also electrostatically repel each other, and the electrostatic repulsion exactly matches the gravitational attraction. So they just sit there for all time. You can put them anywhere you like. So this is the simplest example of a solitonic solution. It's the nearest you can come in 3+1 dimensions to a multi-soliton solution. It's a multi-Blackhole solution, time independent, 0 Hawking temperature, and it will stay there forever.
What was their way of getting?
Sorry?
What was their logic again?
Oh, they actually solved the equations of motion with the ansatz I started with this. And they actually managed to solve the equations of motion.
The real identity is harmonic, then you can do it. I mean, essentially the equation of motion, if you just plug in this h and you write the metric in this way, and you massage it, h becomes, I mean, the equation of motion just also h is equal to.
So they made a guess that this was a sort of interesting ansatz. I'll say more about it. It's okay.
It's complicated because, you know, to realize, because, you know, if the usual resonance to black hole is written in a different ansatz without the flash transfer,
Right.
but, you know, they just realized that. And this is before supersymmetry was known. I mean, this is long before anybody knew anything about supersymmetry. They just, you know,
But what you're supposed to be impressed by, in the sense, is this is multivariable. This has you know, doesn't even have axis symmetry necessarily, and I managed to get a solution with very little work. Whereas if you remember what I said about getting Kerr solution, it took 43 years, and that's that's got axis symmetry. This is just static, and that's the story about supersymmetry. If you look for the supersymmetric solutions, it's a first order system, and it's usually much easier, and you get some very, very instructive constraints, which then tell you when you plug in, you do the one equation of motion that you need to do, and you get an answer. So I'm not going to do the supersymmetry analysis for the Microstate geometries in general, but it has exactly the structure again. We're going to see a bunch of constraints that supersymmetry tells us have to be there, and then there's going to be one equation of motion, and then we'll get exactly the system we need. But this is as an illustration. I went through it in great detail because you can do it easily in a blackboard. But it's very, very generic structure, and I think I'll stop in a few minutes, but next time I will actually pull out the threads that I really want to use to generalize. Yeah, sorry.
I'm confused by mass equal charge because they are dimensionally different.
Oh, there's some epsilon naughts if you want to. I'm using units where charge is measured so that works.
So there is a conversion. There is
1 over 4 pi epsilon. There's a 1 over 4 pi epsilon naught, so I choose epsilon units where epsilon naught is 4 pi. Okay, or 1 over 4 pi. I put it in the notes. I actually checked. I really did. It's in the notes. Normally we take units of charge such that mass equals charge makes perfect sense. And it means you take
usually when you
Faraday.
have the maximum repulsion and the gravity attraction to be the same. So that's
The Faraday constant
Well,
is
it just
liable
means
to be the same as the Maxwell constant.
electrons, for example, have more charge than mass. So, you know, in a sense, you know, things just fly apart because, you know, things which have more mass than charge attract each other. So.
I think I should probably stop. I put a little remark in the notes, but I want to maybe I'll save this for next time. There's another theorem I'll pick it up next time, which is a little detail, but it's actually goes in the direction of a lot of other work done in the group here. Remember I said there's this data point here. You can actually deduce that a priori. And I'll just make that comment and I'll pick it up the next time. There's this game which we call making sandwiches. Given a killing spin, or giving one of these solutions epsilon, we can start making sandwiches. In other words, you put gamma matrices and make vector fields, or you make tensor fields. So we're making sandwiches. You sandwich gamma matrices between epsilon. These are interesting tensors. It is a theorem that this is always a killing vector. Always. This is the statement that two supersymmetries commute into a translation, or commute into a Hamiltonian, and the Hamiltonian is a symmetry of the system if Q kills it. Therefore, there is a killing vector, and I'll say more about it up next time. But in fact, the fact that, look at this metric, there's only one killing vector, n mu, dx mu, is equal to ddt. That's the only killing vector in the problem. Therefore, it has to be that one. And that determines that. I'll say more about it next time, but I'll say more about making sandwiches later because that's a whole other research thread that you can do. You can ask the question, if I make a supersymmetric system, I find the epsilons, let me make all the sandwiches. What are the relationships between the tensors made out of sandwiches? That's basically all the stuff about generalized structures and generalized complex structures, generalized this structure. That's sort of what Ruben and Mariana do, and there's a beautiful story there. It's a direction I'm not going to take. Anyway, I'll stop there.
And what about the other one? Has some T mu nu?
Oh,
Does it,
that's probably something rather simple. I can't remember what it is, but
does it
when
have some
you supersize
properties?
it's trivial. It's a scalar. It's probably h or something. And when you skew symmetrize, it's probably the curl of this. So you start making these sandwiches, and then you ask, what are the relationship between them? And I think this one is simply the kernel of that one in this case. But in more complicated stories, you get really beautiful structures that are related to each other by first-order differential equations. And so that's a whole, you can say, I don't like dealing with spinors, I just want to deal with the tensor fields that come out of spinors. And then you can turn all of these questions I'm talking about here into questions about those tensor fields. I'm not going to go there. Okay, let me stop there. Hello. The notes.
I wrote the URL of the website of the course.
And I've already written the next chapter, which is next lecture or thereabouts. This chapter is kind of long because I didn't know where I was going to go, what I was going to pick and choose. The next chapter, I've got one theorem I want to prove. I want to prove the no solitons without horizons theorem and show where the hole is in the theorem, and then prove the no horizons without no solitons without topology theorem. And all it requires is differential forms and basically this kind of electromagnetism coupled to gravity. And so we'll go through that. Yeah.
Then we meet in 5 minutes for those that want to go for lunch.